So we have seen what our matrix S is and what is S conjugate and what these matrices do to a vector X. So we will talk about the eigenvalues and the eigenvectors of these matrices in a bit. But first we have to look at a very important, we have to actually know a very important property of matrices is that if there are two matrices A, B that commute, that means if A times B is equal to B times A, that means they are commuting, then these two matrices A and B, they have the same eigenvectors. Okay, and the second property is that we have seen what our S and S conjugate matrices are and what is a circular matrix. If C is a circular matrix and we have the matrices S, then this is a property of circular matrices and the matrices S is that they actually commute. So we know that C and S have the same eigenvectors, but their eigenvalues may differ, and they will differ as we will see. So with that property, now if we can find the eigenvectors of S or S conjugate, then we can find the eigenvector of C, the circular matrix, and then we can find the eigenvalue of the circular matrix. So we will work out this way. Now let's say we are trying to get the circular matrix, trying to get the eigenvalues and the eigenvectors of S. So from the definition of eigenvectors and eigenvalues, we know that W will be an eigenvector of S if you can write this equation where lambda is the eigenvalue. Also, we know that if we multiply, from the, let me explain this way. What we're doing with the eigenvector and the eigenvalues is that eigenvector is such a vector if we multiply the matrix S with its eigenvector W, we are actually multiplying a scalar quantity with that eigenvector. Okay, lambda is just a scalar quantity. It can be complex, it can be real. So if we multiply this quantity with S again, what we're doing is that we are again multiplying this quantity with the eigenvalue. So we'll get this, or we can write S square lambda square W. So in general, we can write S to the power L, any power L, lambda raised to the power L times W. So with these quantities, we can move on to the next equation. So again, we have to remember what S was doing. S was right shifting the vector, circularly right shifting the vector W. So if we write W this way, W naught W1 dot 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 Wn minus 1, let's say W is an n element vector, and we have lambda W1. So what's this doing? This is, let me put on vibration. Okay, this is just right shifting. So we got this, and then lambda W1 W4. Okay, so what we can write from here, we can see if from on the left side, we for any WK we'll get here WK plus 1. Okay, for n minus 0 it's n, for 0 it's 0 plus 1 1. So I will describe this one in a moment, because for that one Wn minus 1, if we put k equal to n minus 1, then it's lambda times Wn equal to lambda times W0. So I will describe that in a bit. Okay, let's talk about that in the next video.